other neuron, it can contact the muscle, and so on. However, we mentioned that chemical do move inside the axon in both directions. Okay, if they move from the cell body to the axonal terminal, we call that anterograde. If the material moves from the axonal terminal back into the cell body, we call that retrograde. I remember we talked about the dog. Remember that?
Yeah.
Okay, we find out that that's the reason why. Why do the neuron have to transport the waste product way distant away, all the way back to the body to be disposed? Because the environment needs to be at the optimal condition for the neuron to work. Neuron cannot afford to dump all the trash right there. That creates the environment where they cannot conduct electrical signal. And that's the whole point I want to get. Think about it, you guys, because we know this. Long time ago. Right now we learned already that if this muscle control right here, the muscle that flexing your thumb, where is that muscle? The muscle that flexing your thumb? Where? Okay, somewhere in your forearm, am I correct? Okay, so that muscle is right here. There is a motor neuron from the spinal cord will control that muscle, right? And at first, when they study, they say, okay, that muscle right there, they just wonder at what level of spinal cord and where in the spinal cord that this motor neuron locate that control that muscle. That's a wonderful question, isn't it? You know, they know this. And in the past, you know how they find out? They look at the muscle and they find out the NMJ on that muscle and they inject the dial into the NMJ. You say, yeah? They know that all the waste product will be taken up at the axonal terminal and transport back to the cell body. So the axonal terminal will pick up this blue dial and transport back into the spinal cord. And after that, a little bit, and they look at it in the spinal cord. Where is the spinal cord turn blue? That's where the axon and the neuron that control that muscle located at. Is that cool? So that's why, because of that, we're able to know that. No, I don't know anything about this. Go away. Okay. And that's how we're able to map out. That's how we're able to know that any segment in your spinal cord injury, what muscle you cannot control, or vice versa. If you cannot move your finger or do something like that, where that nerve damage occurs, just because of this concept. Really fun. And vice versa. I'm studying the spinal cord. I just wonder, this neuron, what does it do? What muscle it contract? I can artificially stimulate that neuron, and I see what muscle move. Oh, I stimulate that neuron, that muscle move. Oh, that is a neuron control that muscle. And the whole thing has been mapped out. The whole map has been mapped out already. And that's how we're able to know when the nerve damage, what will be the effect of that nerve, and then so on. Okay? We did talk about myelin sheaths, right? The myelin sheath, because it's, one more time, let's see, you study. Both the neuron in the CNS and in the PNS, they have myelin sheaths, right? But the cell make up the myelin sheath is different. What cell make up the myelin sheath in the CNS? The name is very romantic. Oligodendrocyte. But the cell that make up the myelin sheath in the PNS, we call that Schwann cells. Okay? And they make up the content, make up purely by the fatty material, and that's why you learn later there's a term we call white matter and gray matter in a minute. Okay? And by the way, did you guys get to the nervous system in the lab? Okay? And we have the model I call the neuron model. That neuron model has the cell body and the axon on it. Okay? And you see that the myelin sheath can become really thick. Why do we need the myelin sheath on the axon? Protection, extra layer. Secondly, that it insulates electrical signal so that electrical signal does not short circuit and affect the other axon that you do not intend it. Okay? We also find out that without the axon, without the myelin sheath, the speed of electrical signal will not be as fast. So the more myelin sheath that present in the axon, the faster that electrical conducting occurs. Based on this concept, which they do not mention in the book. Therefore, when we look at the nerve fiber in our body, based on the evaluation of the myelin sheath and based on the diameter of the axon, they divided the nerve fiber into 3 types in general. We call them type A, type B, and type C. In general, okay, type A is usually conduct electrical signal 400 meters per second. That's really fast. where C fiber between 2 and 4 millimeter per second. That's how fast the electrical travel. And B fiber are somewhere between 400 and 4. So based on that, if I ask you, which fiber have the most violent sheet? We have three choices, A, B, and C. Which one do you think have the most violent sheet? The faster conductor, right, which is A. Which one have the least violent sheet? C. As a matter of fact, C almost have none of the violent sheet. And that's what you see right there. To give something to think about. You know our pain, the pain receptor, the nerve receptor, the nerve that carry pain sensation that report to the brain, most of them belong to the type C. What does it mean, the type C? For example, if you touch something really hot, by the time you realize that it's really hot and you withdraw your hand, you already burned. Right? Because it's carried by the C fiber, therefore, it carried by the C fiber, therefore, the signal is lower. And here's another one we find out that we find in the ICU. People in ICU, you know, they have critical condition, and some people actually, we quote unquote, die. They have stopped momentarily, and then we revive them, they're coming back. When they're coming back, sometimes they say that, I was in a stage. Remember, this guy has tube and needle throughout the body. Okay, they're in the ICU, but he say, I'm in the stage that I don't feel any pain. And you guys get me back. What do you do? How do you explain that? When you say, this person have needle and IV and everything throughout the body, and you say, feel no pain at all. You feel elated somewhere that there's no pain. What we try to explain them? Go ahead. Go to the what? No, it's even more than that. It's almost like, you know, peaceful. And there's no pain. They didn't feel any pain at all. Okay? And what we try to explain in terms of theology is this. When you are dying, okay, what nerve fiber will die first? You have three choices, A, B, and C. Which one have the least protection? C. Does it make sense? C fiber die first. And what information usually C fiber carry? Pain. So that's why we think that when you are, whatever you did, okay, it is the C fiber that started to degenerate, therefore the pain sensation no longer reach your brain. And that's why people say they don't feel pain. If you want to find more to ask, do you see the light in the tunnel? Or something like that, ask. But yes, and that's the reason why pain takes a little time for you to perceive. It's not as fast as the other sensory. Cool, huh? Not necessary, but it could be thinner. Okay, balancing yet. Actually, do not. Every single tissue in our body as we age, they will reduce the chance. But you don't see like a bone, we talk about bone or muscle, when you get older, they really shrink. But your myelin sheet, just slightly, it's still myelin sheet, it's there, it's a little bit thinner. Okay? We thought, oh, maybe that's the reason why as we get aging, we don't think it fast, that's different. Okay? It's a connection that the reduced function is not myelin sheet. So you know already that if I ask a question, true or false, all axons in the human nervous system have myelin sheet. The answer is no. No, there's no myelin sheet. We just tell you guys that C is one of them, right? And that's why we have the term unmyelinated and myelinated. Okay, so yes, there are some axons in the body do not have myelination at all. Have we talked about nerve Ranvier? Okay, nerve Ranvier is constriction that occur along the myelin sheet where you can see the bare axon. Okay,